A buildup of magnetic energy within a star leads to a massive solar flare, lashing outwards into the cold of space. A distant supergiant begins to fuse iron within its core, setting off a chain reaction that will tear it apart completely in a spectacular hypernova. And pressure builds up within a rapidly spinning magnetar, causing a starquake on its surface that releases a super-powered gamma-ray burst. These are all examples of cosmic tipping points, moments when the universe snaps. The material that makes up planets, stars, galaxies, and even ourselves may appear stable, but it all teeters on a delicate tightrope. From the tiniest atom to the largest supercluster, push anything beyond a critical tipping point, and chaos ensues. Yet there is often salvation. Almost always, some subatomic safety net kicks in to wrestle back stability and prevent complete destruction. A way for Jekyll to keep Hyde in check. And nowhere is this more true than inside neutron stars, the final barrier before cosmic oblivion, the most extreme object possible within space and time. Tiny, incomprehensibly heavy dead stars that spin at dizzying speeds, their very existence strains the laws of physics. The gravity on their surfaces is so strong that mountains can only form fractions of a millimeter high, and if you dropped something, it would reach half the speed of light before it hit the ground. And yet somehow, they only get more extreme as we explore deeper, and the bizarre secret of what dwells in their center, where matter is put under pressures seen nowhere else in the cosmos, may even force us to rethink what we understand about the universe itself. They are the ultimate physics experiments, forcing ordinary matter into extraordinary situations that teeter on the edge of oblivion. To understand the interior of neutron stars is to understand the true nature of reality. And so, just how far can you push the universe before it breaks? Four years ago, I started the entire history of the universe with a simple roadmap of the first 7 or 8 videos, all within the first second of existence. And this month, we hit 1 million subscribers and have since covered 13.8 billion years and beyond. It's been amazing to see it grow and hugely gratifying to see such a big appetite for our universe out there. But what would your passion project be? Whether you want to create documentaries, a podcast, a company that sells services, or a brand that sells products, Squarespace can help. Squarespace is super simple to use and easily allows you to build a totally unique online presence for your project. Their design tools are cutting edge, featuring a huge library of professionally designed and award-winning templates, customizable with easy drag and drop editing. The different style options are excellent. Indeed, Squarespace is known for creating visually stunning websites in very little time. Their analytics tools are also great. You can review website traffic and easily learn where to focus engagement. And their automated email campaigns can help you stay connected and grow the community that loves your project, whatever it is. So head over to squarespace.com/history of the universe to save 10% off your first purchase of a website or domain using the code history of the universe and get started on your passion project. What are stars made of? It is Christmas Eve, 2024. While those of us on Earth are knee-deep in merriment, the Parker Solar Probe is shattering records. Hurtling through space at a staggering 200 kilometers per second, it swoops to within 6 million kilometers of the sweltering solar surface. It is the closest any human-made object has ever dared to venture to our Sun. 6 million kilometers may sound a long way, but it's enough to place Parker inside the Sun's outer atmosphere, a wispy, gossamer layer known as the corona. It is from here that the Sun launches its tirade of coronal mass ejections, mountain-sized bombs of subatomic shrapnel that can cause widespread power cuts if they reach Earth and overwhelm our magnetic field. Drop below the corona and you'll find a thin layer called the chromosphere, roughly 5,000 degrees Celsius, just before you reach the visible surface of the Sun, the photosphere. The photosphere is constantly roiling and churning as superhot material bubbles up from the cauldron below. It is an arresting image, but to truly understand this bizarre alien environment, what it's actually made of, and indeed what the interior of our own Sun means for the mysterious cause of neutron stars, we have to go back in time more than a century before the Parker Solar Probe was even conceived of. To Calcutta, India. Lord Curzon sits hunched over a map of southern Asia, his sweat dripping onto archipelagos and peninsulas. As Viceroy of India in 1905, he's the direct representative of the British Crown in this part of its sprawling empire. And he has a growing problem. Bengali and Indian nationalists are becoming increasingly vocal with their dissent against the British Raj. Curzon's eventual solution to partition Bengal along religious lines, creating West Bengal for Hindus and East Bengal for Muslims. It is a disastrous move, only serving to swell levels of discontent, leading to boycotts of British produce. And among those affected is teenager Meghnad Saha. Born to a poor family in Dhaka, now part of Bangladesh, he'd earned a full scholarship to the British-run Dhaka Collegiate School, but was expelled due to his participation in these protests. The episode obviously had a profound impact on Saha as he remained actively involved in politics for the rest of his life, an avid champion of Indian independence. But Saha's expulsion was only a temporary setback in a flourishing academic career, and by 1923 he'd become a professor at the University of Allahabad. And today he is most famous for his work on the Saha ionization equation, thanks to which astronomers can take the local temperature and pressure and calculate how much of different parts of our Sun is ionized, and therefore what state of matter they are made up of. In physics, ionization is the process of destroying atoms, pushing them beyond a tipping point. In the most simplistic depiction of an atom, negatively charged particles called electrons orbit around a central, positively charged nucleus. Although far from a perfect analogy, you can think of this as similar to planets orbiting around the Sun. Whole atoms are electrically neutral, with the opposite electric charges of the electrons and the nucleus cancelling each other out. These opposite charges also provide an attractive force that keeps the electrons in orbit. Give these electrons an energy boost, however, perhaps by raising the temperature, and they suddenly have enough energy to break free from their subatomic shackles. Like India breaking away from colonial rule, the electrons have declared their independence. In the language of physicists, the material has been ionized. The result is an electrically charged soup of electrons and atomic nuclei, known as a plasma. We learn at school about 3 states of matter: solids, liquids, and gases. But there are more, and plasma is just one of those that we will encounter on our journey into the center of neutron stars. And so the Saha ionization equation tells us that despite a temperature of around 5,500 degrees Celsius, the photosphere of the Sun is actually not hot enough to rip electrons away from every atom. Instead, the photosphere is only partially ionized, a mixture of hot gas and plasma. We have to dive deeper to find a region where plasma truly rules supreme, a place where temperatures rise to at least 10,000 degrees Celsius. By the time we reach the inner quarter of the Sun, we have entered its core, and it's hard to do justice to just what an extreme and extremely dense environment we have now crossed into. The sheer weight of all the layers above crush down on the center of the Sun with unimaginable force. The plasma is squeezed together to such a degree that the density climbs to 150 grams per cubic centimeter. That's nearly 8 times denser than gold despite the core largely being made of ionized hydrogen, the lightest element in the universe. If you were to fill up an Olympic-sized swimming pool with core material, it would weigh more than the Titanic, complete with all its passengers and cargo. Of course, if gravity had its way, the Sun's core would buckle under the strain of this incredible pressure and collapse. But it doesn't, and instead the Sun will stay stable for many billions of years, carefully walking an invisible, internal tightrope. And so if gravity is the astronomical equivalent of a destructive Mr. Hyde, then what plays the counterbalancing role of Dr. Jekyll? What keeps the Sun from crossing its tipping point? In the Sun's core, hydrogen is squeezed so tightly that it fuses into helium. Every single second, 620 million tons of hydrogen disappear and 616 tons of helium emerge. The missing mass is converted into energy, meaning the Sun generates the equivalent of 4 million tons of sunshine every second. Yet the Sun is so dense that it takes an average 170,000 years for this light to battle its way to the solar surface. And it is the outward pressure generated by this nuclear energy, along with the searing heat of the core, that prevents the Sun from collapse. This delicate balancing act between outward pressure and inward gravity is known as hydrostatic equilibrium. Physicists and astronomers calculate it using something known as the equation of state. It describes the intimate interplay between temperature, pressure, and the density of material in the various layers of a star. A softer equation of state makes the core more compressible. A harder one offers up a greater resistance to gravity. Remember these. Equations of state will become a central pillar in our quest to understand the inner workings of neutron stars. Remarkably, astronomers know the equation of state in the core of the Sun to a very high level of accuracy, even though they can't see the core or get anywhere near it. And it is one particularly elusive type of subatomic particle that offers up invaluable assistance in this effort: the neutrino. The Sun's core produces prodigious amounts of neutrinos as a direct byproduct of fusing hydrogen into helium, a staggering 179 trillion every second. They pour out of the Sun and spread far into the solar system. Indeed, hold your hand up to the Sun and the number of solar neutrinos that stream through your thumbnail in a single second is higher than the number of people on Earth. The total number of neutrinos that will pass through your body over the course of your life is roughly equal to the number of stars in the entire observable universe. But the number of neutrinos produced in the Sun's core is remarkably sensitive to the local equation of state and temperature in particular. Tweak the temperature within the Sun even slightly, and the number of neutrinos swings dramatically, making solar neutrinos the perfect thermometer for measuring the temperature of the Sun's core, a whopping 15.7 million degrees Celsius. Understanding the Sun in this way is vital work, with far-reaching consequences. Indeed, the Sun is by far our nearest star, some 265,000 times closer than the next. This means that astronomers use the Sun and its equation of state as a benchmark for all the other stars in the universe. And so it is the ideal starting point for understanding how the equation of state changes when stars die. For the Sun may walk the tightrope of hydrostatic equilibrium for billions of years, but nothing lasts forever, even stars. Eventually, the Sun will exhaust the fuel in its core and those nuclear reactions will cease for good. With Hyde trumping Jekyll, at least temporarily, what happens next is guaranteed to be spectacular. And in some stars, these spectacles of destruction lead to the creation of something truly bizarre. Acrid black smoke billows as seawater surges through every part of the ship. It takes just 2 minutes for the 12,000-ton French battleship to sink beneath the waves. The sinking of the Bouvet on the 18th of March 1915 marked the start of one of the worst Allied defeats of the First World War. The battleship was part of a fleet tasked with sailing down the Dardanelles Strait, one of the narrowest in the world. The plan was to lay siege to Constantinople, now Istanbul, and force the Ottoman Empire, a key German ally, out of the war. Yet the sinking of these 3 ships, including the Bouvet, left Allied naval commanders with little choice but to turn and run. A new plan was hatched to stage a series of amphibious landings and take the peninsula on foot. Over 500,000 Allied soldiers would land on the coastlines around the Dardanelles. 57,000 of them would never make it home. And among those seriously wounded at Gallipoli was 26-year-old Royal Marine Artillery officer Lieutenant Ralph Fowler, who took a bullet to the shoulder. While that Turkish bullet did little to change the course of the First World War, it ended up playing a pivotal part in changing the way we would come to understand how massive stars change into neutron stars when they die. Before the war, Fowler had been a mathematician at Cambridge, yet it was while convalescing from his shoulder wound that he met Army captain and biophysicist Archibald Hill. Had Fowler not been shot, it's unlikely the two men's paths would ever have crossed. Hill recruited Fowler into his notorious team of scientists and engineers, which came to be known as Hill's Brigands. Other members of the ragtag bunch included Charles Darwin's son, Horace, and Arthur Milne. As part of the Brigands, Fowler made such significant contributions to anti-aircraft ballistics that he was made an officer of the British Empire in 1918. More than that, though, Fowler's work inspired him to turn his attention away from pure mathematics and towards physics. And his ensuing discoveries would become so important that, upon his eventual death in 1944, Indian astrophysicist Subramanian Chandrasekhar would write, "His work, characterized by a rare combination of physical insight and mathematical precision, shows what theoretical astrophysics at its best can be." In fact, Chandrasekhar would later win the Nobel Prize for a discovery that would have been impossible without the groundwork laid down by Ralph Fowler. A discovery that revealed that one of a star's many tipping points, in actual fact, can be breached, with particles placed onto a new and even more precarious subatomic tightrope. Fowler and Chandrasekhar's discoveries were centered on the inner workings of a peculiar type of star. Look up at the winter night sky from the northern hemisphere, and one star in particular will instantly grab your attention. Not only is it the brightest, but it twinkles violently through a wide range of vivid colors. Its name is Sirius, the dog star, and has reached far and wide across human culture. Indeed, it is the source of the phrase "the dog days are over," which traces its origin back to Roman times. The dog days end in July, when Sirius starts rising with the sun and so disappears from the night sky. But Sirius is not a lone wolf. It has a companion, referred to as the pup, with the two stars pirouetting around one another every half a century. In the years following the First World War, the true nature of the pup was a confounding mystery. For one thing, this star was smaller than the Earth, but somehow still hotter than the Sun. In 1922, Willem Jacob Luyten gave these exotic objects a name: white dwarfs. What could they be made of? One thing was clear. To pack a star's worth of material into the space usually occupied by a planet, white dwarfs must be extremely dense. Indeed, each cubic meter tips the scales at 1 billion kilograms. A sugar cube of white dwarf material weighs as much as an elephant. A shipping container's worth matches the mass of the Great Pyramid at Giza. By all rights, something so dense should buckle and collapse. In the Sun, it is the outward thermal pressure that resists the inward pull of gravity. Yet in a much denser white dwarf, this pressure alone would not be strong enough to shore up the star. What else could be keeping Hyde from the door and stopping the pup from falling in on itself? It would be Ralph Fowler who provided the answer, alongside two Arthurs, fellow Hill brigand Arthur Milne and legendary astronomer Arthur Eddington. It turned out the matter inside white dwarfs is degenerate, a cutting-edge concept back in the 1920s. Indeed, that decade may be most famous for the roaring of jazz, flapper girls, prohibition and speakeasies, but it was also an amazingly fertile time for new physics. Physicists were just getting to grips with the implications of a revolutionary new branch of science, quantum mechanics. For the 1920s was also the decade of Schrödinger, Heisenberg, Bohr, and Pauli, and it is the latter's exclusion principle that lies at the heart of degenerate matter and the secret of what white dwarfs, and in turn neutron stars, are made of. Quantum mechanics gets its name from the fact that in the atomic world only certain quantities are allowed. Subatomic particles, for example, are only allowed to have certain energies. Those that share the same energy must have some other property to distinguish them so that no two particles are ever completely identical. There are only so many alternative properties that they can have, meaning space within each permitted level of energy is limited. And to see how this works in practice, picture the Chrysler Building in New York. Imagine that each floor of the skyscraper represents one of the energy levels that particles are permitted to have in the quantum world. Crucially, like real skyscrapers, each floor has a maximum capacity that it's legally allowed to hold. Anyone else who subsequently tries to get in is excluded, hence why it's called an exclusion principle. Inside the Sun, for example, particles are spread out enough to never trouble the maximum capacity limits. Yet when material is crushed down into the extreme densities found inside white dwarfs, the situation changes. Quickly, the ground floor fills up, then the first and the second. No matter how hard gravity tries to squeeze more particles down into these lower floors, the rules of quantum physics forbid it. And it is this that offers up a formidable resistance to the inward pull of gravity, and it is this we call degeneracy pressure. This was Fowler's big insight, one he has arguably not recognized widely enough for today, his relatively early death meaning he never received the Nobel Prize that he most likely deserved. Today, we know that white dwarfs form when stars like the Sun die. After death, half the mass of the star ends up crushed to extreme densities, forming a white dwarf. The other half is shed like a snake's skin, puffing out into an intricate and spectacular cloud called a planetary nebula. Indeed, this is the fate that awaits our own Sun in around 7 billion years' time. But for the most massive stars, however, an entirely different fate awaits. Let's return to the night sky. If you start at Sirius and move up and to the right, you'll soon stumble upon the famous trio of stars that makes up Orion's belt. Continue along the same line, and before long, you'll hit a group of stars that resemble the letter V. You've arrived at the Hyades cluster, a group of stars that represents the head of Taurus, the bull. The animal's horns begin to protrude from the top of each prong of the V, and at the top of the left horn, close to the star Zeta Tauri, lies the Crab Nebula, one of the most famous clouds of gas and dust in the sky. The Crab is a supernova remnant, the smoked-out ruins of a once mighty star. In 1054, Chinese astronomers wrote of the appearance of a brand new star in the sky, a guest star. It was visible during the day for nearly a month and took 2 long years to fade from the night sky. To label these events as merely super is to do them a major disservice. Indeed, in just a few seconds, a supernova emits more energy than the Sun will in its entire multi-billion-year existence. Nor are they particularly rare. A supernova is thought to detonate somewhere in the universe every 10 seconds, meaning more than 100 have exploded since you started watching this video. Yet it's what lies at the heart of the Crab Nebula that is arguably even more impressive. A neutron star. If white dwarfs seem incredulously dense, neutron stars are 100 million times denser still. A mere tablespoon of neutron star material weighs more than the combined mass of all 108 billion humans who have ever lived. If white dwarfs are similar in size to the Earth, neutron stars are the size of cities. The neutron star at the heart of the Crab is just 21 kilometers across. That makes it about the same size as London and significantly narrower than Tokyo. More than a sun's worth of mass living cheek by jowl in unimaginably cramped quarters. The gravitational pull of a neutron star is understandably immense. To beat gravity and power away from the Earth, you need to travel at a speed of 11 kilometers per second. The equivalent escape velocity of a neutron star is 150,000 kilometers per second, or about half the speed of light. On Earth, gravity is feeble enough to allow mountains like Everest to tower to almost 9 kilometers above the surface. On a neutron star, however, the tallest mountains are less than a millimeter high, making them some of the smoothest objects in the universe. They also spin at dizzying speeds, with the Crab's neutron star rotating 30 times a second. And mass wasn't the only thing concentrated down when the original star went supernova. Its magnetic field was too. A typical neutron star has a magnetic field that's 100 billion times stronger than a fridge magnet's. This often corrals beams of radiation that surge from the neutron star's poles. When Earth is hit by volley after volley of this radiation, we hear a series of pulses. So we also call these objects pulsars, a fudging together of the words pulsating and star. Chandrasekhar's great discovery was to show that Fowler's degeneracy pressure can only support a white dwarf up to a maximum mass of 1.4 suns. If the core of a dying star reaches this tipping point, Jekyll loses yet more ground to hide. The ensuing collapse forces electrons and protons to merge into neutrons, and a neutron star is born. But neutrons also obey the Pauli exclusion principle, meaning no two neutrons can share the exact same quantum properties. Again, this limits the capacity of each energy level. Once a level is full, even gravity cannot contract the star any further. This neutron degeneracy pressure catches the neutron star. It is the only thing keeping a neutron star teetering a few tens of kilometers from oblivion. From the name, you'd be forgiven for thinking that these enigmatic objects are 100% neutrons. They are not. What's more, the deeper down you go, the more and more mysterious the ingredients to be found there become. Just as with our own sun, the surface only hints at the extremes within. Our journey to understand the true inner workings of neutron stars is really only just beginning, and one of the biggest recent clues came from a neutron star that shouldn't even exist. There's a reassuring click as the astronaut's helmet clips firmly into place. With their spacesuit now sealed, it's on with the backpack that will be their lungs for the next 6 hours. The airlock opens and they glide out into the inky void, only to be hit by a cacophony of colour. The bluest blue is etched with shades of green, yellow and white. The Earth is a magnificent marble floating in the empty black ocean of space. But there's little time to take in the view. One of the many instruments bolted to the exterior of the International Space Station is faulty. NASA recently couriered up a repair kit on one of the ISS's regular supply runs. Now it must be painstakingly fitted by hand. The experiment in question is a washing machine-sized X-ray telescope called the Neutron Star Interior Composition Explorer, or NISA for short. Its thermal shields are 500 times thinner than a human hair and were damaged in May 2023 with the biggest hole the size of a postage stamp. Excess sunlight was spilling onto the telescope, damaging its ability to peer at distant neutron stars. Of course, NISO was never designed to be serviced or repaired in orbit, so its eventual repair in January 2025 proved to be an audacious feat of engineering. Astronomers were desperate to get NISO back to work because before it was damaged, it was starting to provide tantalizing clues about what's really going on deep inside neutron stars. And so to uncover what NISO has found so far, we need to take a journey down through a neutron star's many layers. Hovering above a neutron star's surface sits an atmosphere of hydrogen and helium just 10 centimeters thick. It has a density similar to diamond and is superheated to a temperature of around 2 million degrees Celsius. By the time we reach the crust below, the pressure is so high that electrons are stripped away from atomic nuclei, leaving behind an ionized sea of electrons, protons, and neutrons. The immense forces at work inside a neutron star's crust twist and distort the protons and neutrons into strange and exotic structures not seen anywhere else in the universe. Physicists call the resulting material nuclear pasta. Though its existence remains theoretical, the result of highly detailed computer simulations of matter under extreme duress. Indeed, if it does exist, nuclear pasta would be the strongest material in the universe, some 10 billion times stronger than steel. According to those simulations, nuclear pasta comes in a range of forms, each named after a different type of the Italian foodstuff. Near the surface of a neutron star, the protons and neutrons take on a bubble-like structure that astronomers refer to as gnocchi, after the roundish potato pasta dumplings. As we dive deeper into the neutron star, the pressure climbs and the gnocchi stretch out into shapes resembling spaghetti. Drop deeper still and the spaghetti are squashed into sheets of lasagna. Taken together, these nuclear pasta layers are just 100 meters thick, yet they weigh more than 3,000 Earths. Astronomers thought that they understood the structure of neutron stars fairly well, but back in 2019, the universe threw them a curveball. The most massive neutron stars are supposed to be the smallest. More mass means stronger gravity and a greater ability to crush the star's material into a smaller space. Except this wasn't the case when astronomers used NISO to observe a neutron star known as J0740 plus 6620. They quickly realized that it was one of the most massive neutron stars they had ever found, tipping the scales at just over twice the mass of the Sun, so it followed that it should also be one of the smallest. But it wasn't. J0740 is the same size as other neutron stars with only 2/3 of its mass, and so it quickly became the source of immense debate. The star made no sense. One possible explanation is that astronomers have been using the wrong equation of state. Unlike with the Sun, it's a lot harder to pin down the correct equation of state for neutron stars. There are hundreds of different possibilities to choose from, and detailed observations of neutron stars are harder to come by. Nor can we replicate their extreme pressures and temperatures here on Earth. This means that J0740 could help narrow down the field of possible equations of state, especially as its large size hints that its interior may be less compressible, or squishy, as astronomers tend to say, than they had previously thought. But alternatively, and most interestingly, the lack of expected squishiness could come from further down. Because the mystery surrounding J0740 has forced astronomers to re-examine what might exist deep in the core of a neutron star, below the layers of super-strong nuclear pasta. Before the fuss surrounding J0740, the leading idea was that the core of a neutron star is home to a quark soup. Protons and neutrons are not fundamental particles, but are instead each made of 3 components called quarks. As the pressure intensifies towards the core of a neutron star, The idea was that protons and neutrons would be prized open and disassembled into their constituent quarks. But it takes energy to break the super-strong bonds that hold the quarks together inside protons and neutrons, meaning there would be less energy available to resist gravity. Indeed, that's why more massive neutron stars are supposed to be smaller. But as we've seen, J0740 showed astronomers that this wasn't always true. Particles called hyperons add further doubt. There are 6 types of quark in total, and protons and neutrons are only made up of 2 of them, up quarks and down quarks. The other 4 types are called top, bottom, strange, and charm. Hyperons are particles that contain strange quarks, but no top, bottom, or charm, but have such short lives that they disappear from experiments incredibly quickly, making them hard to study in detail. Some popular neutron star models argue that the intense temperature and pressure found in their cores could not only create hyperons, but also keep them stable for long periods of time. But there is a problem with this idea. The presence of hyperons should soften the equation of state, reducing its resistance to gravity. That would make the interior of a neutron star more squishy, not less. After the discovery of J0740, suddenly the idea of a neutron star's core being made of either a quark soup or strange quark-containing hyperons was on increasingly shaky ground. But what would it mean if the quark soup idea was abandoned? If further studies continue to pour yet more cold water on the theory, what else could lurk in the heart of a neutron star? A big factor that the quark soup models don't usually account for is dark matter. Ever since the 1930s, astronomers have seen many situations where extra gravity is needed to make things make sense. For example, galaxies that spin or move too fast or that bend light too much. One explanation is that the universe is riddled with invisible material that acts as a gravitational glue. It was the Swiss-American astronomer Fritz Zwicky who first coined the term dark matter in a paper published in 1933, and the very next year he was also the first to propose the existence of neutron stars, alongside Walter Baade. And so if dark matter does exist, massive stars routinely plow through it as they move through space. Those stars would hoover up some of the dark matter, which then would sink to their cores. It would then remain there as the core transitioned into a neutron star as the star goes supernova. Indeed, studies have shown that adding some dark matter into the quark soup hardens a neutron star's equation of state. In turn, that provides extra resistance against gravity, potentially explaining why J0740 isn't as small as originally expected. But that is just a mild tweak to the quark soup idea. There is another theory that dispenses with it entirely. One that also traces its origins back to early 20th century India, to a man who worked alongside Meghnad Saha at the University of Calcutta. His name was Sachendra Nath Bose. Born on New Year's Day 1894, Bose was a self-proclaimed perfectionist with a penchant for the poetry of Tennyson. He could have chosen any one of an array of subjects, but chose the path of science, seeing it as a way to boost his country's future prosperity. The best place to study science in India was at Presidency College in Calcutta, and Bose secured one of the coveted 32 places, despite there being 2,000 applicants. Several years later, Bose began collaborating with Saha. Together they translated Albert Einstein's papers on relativity from German to English, so that they could be read by Indian students. By 1924, Bose had moved to Dhaka, the East Bengali city where Saha had grown up. And that year, Saha returned home to stay with Bose, the ensuing conversations leading Bose to develop new ideas about the behavior of certain subatomic particles. However, struggling to get his ideas published in English journals, Bose took a gamble and wrote to Einstein directly. Respected Sir, I have ventured to send you the accompanying article for your perusal and opinion. I am anxious to know what you think of it. It was a bold move, and one which paid off handsomely. Indeed, Einstein was so taken with Bose's insights that he translated them into German himself and had them published in a prestigious academic journal. The work the two men would do together would become known as Bose-Einstein statistics and quickly lead to the prediction of the existence of an entirely new state of matter, the Bose-Einstein condensate. Today, physicists divide subatomic particles into two camps. There are bosons, named after Bose, for example photons of light, and fermions, named after the Italian-American physicist Enrico Fermi, for example protons and electrons. What distinguishes them is a property called spin. The spin of bosons is always a whole number. By contrast, the spin of fermions is usually equal to a half. Crucially, this spin also has a direction associated with it, most commonly up or down. The Pauli exclusion principle that we've already encountered strictly applies to fermions. Two protons or neutrons, for example, cannot be in the same place at the same time. But in a Bose-Einstein condensate, however, all the bosons move together at the same speed, behaving as if they are one giant particle. If bosons pair up in the core of a neutron star with the spin of the two parallel to one another, that could harden the equation of state and provide an outward pressure against gravity. A new form of safety net that keeps Hyde from the door. And this has led some astronomers to suggest that the most massive neutron stars, those weighing at least 2 suns like J0740, could in fact be Bose-Einstein condensate stars. Whatever it's made of, J0740 remains one of the most massive neutron stars ever discovered. But just how heavy can a neutron star get? And what happens if that mass is somehow exceeded? Is there another safety net to catch it? Thud, thud, thud. With what little strength he has left after months of malnutrition, Mikhail Volkov swings an axe and hammers it into yet another tree trunk. The branches sway in their battle against gravity before finally admitting defeat and coming to rest on the hard, frozen ground. Volkov is imprisoned in one of Joseph Stalin's notorious gulags. Like millions of other Soviets, Volkov arrived at his Arctic prison in 1936 at the start of Stalin's Great Purge. He would never leave, dying there a few years later. But it needn't have been this way. In 1924, he'd left the Soviet Union for Canada with his young family in the hopes of a brighter future. However, struggling to find work in Canada, relatives had assured him that things weren't so bad in the Soviet Union after all. He returned, and his fate was sealed. Thankfully, though, he had left his family behind. When Mikhail entered the Gulag in 1936, his son George was 22 and still living in North America. In fact, that very year, George became a graduate student at the University of California under the tutelage of legendary physicist Robert Oppenheimer. The pair would later work together on the Manhattan Project to develop the atomic bomb during the Second World War. However, it was for their earlier work, published 7 months before war broke out, that George Volkov is most remembered today. Along with Richard Tolman, the pair calculated the maximum possible mass of a neutron star, known as the Tolman-Oppenheimer-Volkov or TOV limit. Their initial calculations pegged this upper bound at just 70% of the Sun's mass, a mere half of the Chandrasekhar limit for white dwarfs. However, astronomers now think that this was a severe underestimate. Indeed, the 1990s brought fresh calculations of a neutron star's equation of state, and with them, astronomers drastically revised the TOV limit upwards to between 2.2 and 2.9 solar masses. But to narrow the limit down even further, would require a thoroughly modern piece of technology. In the summer of 2017, the astronomical rumour mill went into overdrive. It all started when astronomer Craig Wheeler put out a cryptically worded tweet on the 18th of August. "New LIGO source with optical counterpart. Blow your socks off." Internet sleuths scoured the public logs of major telescopes, finding that several of them had been hastily diverted to stare at the same galaxy, NGC 4993, 140 million light-years away. But it took 2 further months for astronomers to officially let the cat out of the bag. When Wheeler referred to LIGO, he was talking about the Laser Interferometer Gravitational Wave Observatory in the United States. For the day before Wheeler's tweet, it had picked up a signal for the history books. 2 neutron stars had collided in NGC 4993, and all hell had broken loose. 70 different observatories spread across all 7 continents and in space had picked up the after effects of this collision. For its part, LIGO detected the gravitational waves that washed up on our celestial shore. Just as swimmers, boats, and dolphins moving through water create waves, so objects moving through space create gravitational waves. They are ripples in the very fabric of space itself. This was the first time astronomers had detected gravitational waves from colliding neutron stars. The size and frequency of the waves shot up as the 2 stars death spiraled inwards and collided. Poring over the data, astronomers were able to rule out equations of state that were incompatible with the gravitational waves they observed. This allowed them to narrow down the TOV limit to between 2.01 and 2.17 solar masses, although even that's far from certain. For one thing, the most massive neutron star ever found, PSR J0952-0607, has a mass of 2.35 solar masses, seemingly breaching the proposed TOV limit. But as is often the case, the devil is in the details. The simplest TOV limit applies to neutron stars that don't rotate. However, most neutron stars do rotate, which would nudge the limit slightly higher. But what happened when these neutron stars came together? The combined mass of the 2 neutron stars involved in the 2017 collision was 2.8 solar masses, a clear breach of the TOV limit. When the total mass exceeds the TOV limit, even degeneracy pressure is not a strong enough safety net in the perpetual contest between Jekyll and Hyde. So what happens next? Is there another level of density before oblivion? That is still an area of fevered debate, and one really with only 2 possible outcomes. Yes or no. One theory is that when the neutrons are squeezed together, they burst into a sea of quarks, creating a quark star. Calculations have shown that an object made of strange quarks is the most likely to be stable, so these objects are also sometimes known as strange stars. Fittingly perhaps, strange stars would have some rather odd properties. If 2 strange stars collided, they might produce quark nuggets, also known as strangelets. With masses between 100 grams and 100 kilograms, these clumps of strange quarks would be the astronomical equivalent of zombies. They would convert anything they touched into strange matter as well. Indeed, at one point, strangelets were even considered a candidate for the mysterious dark matter that seems to hold the universe together. While astronomers have never actually seen quark stars or quark nuggets, there are ways that they could reveal themselves. Experiments such as IceCube, located deep beneath the Antarctic permafrost, might be able to spot the subatomic shrapnel produced when quark nuggets strike the upper atmosphere. But if colliding neutron stars don't collapse into quark stars, then there really is only one other possible alternative: a black hole. A black hole is what you get when gravity breaches a star's last critical tipping point. Jekyll no longer has any way of keeping Hyde in check and must, finally, admit defeat. The star's core collapses completely until everything is squeezed down into an infinitely small speck known as a singularity. And it is here that the very laws of physics break. Space and time cease to exist, and with them go our powers to describe what is happening. At least, that's the situation according to Einstein's general theory of relativity, our most lauded and well-tested theory of gravity. But general relativity isn't the only show in town. As we've seen, it's quantum mechanics that so beautifully describes how white dwarfs and neutron stars manage to stay one step away from oblivion. You can't just throw that theory out the window once two neutron stars collide. But the trouble is that general relativity and quantum mechanics are famously quarrelsome. The way they describe the universe is fundamentally incompatible, and both cannot be correct. One or both are likely to be mere approximations to a deeper, more sophisticated theory of quantum gravity. And so, which of the two is likely to blink first in this great game of cosmic chicken? Intriguingly, neutron stars may just hold the answer. The 2017 collision, known as GW170817, was the first time that astronomers had seen gravitational waves and light emitted from the same celestial event. Picking up more than one type of signal from the same event like this is known as multi-messenger astronomy, and GW170817 was arguably its modern debut as an established astronomical tool. 2 seconds after the waves from GW170817 arrived, astronomers also spotted the searing flash of a gamma-ray burst in precisely the same patch of sky. The gap between the two signals tells astronomers how fast the gravitational waves hurtled towards us, and the 2-second gap was consistent with the speed predicted by general relativity and inconsistent with several other alternative theories of gravity, helping to rule them out. A triple star system, known as PSR J0337+1715, provides yet another test. This unusual system contains a neutron star white dwarf pair that not only orbit each other, but together they both orbit another white dwarf. General relativity makes strong predictions about the shape of these entwined orbits, and so far it has passed all of these tests with flying colours. However, press most physicists and they'll venture that general relativity is more likely to break before quantum mechanics. Perhaps we haven't seen general relativity crack yet because we haven't seen it under extreme enough duress. Indeed, that's what makes the center of neutron stars and finding the correct equation of state such a fertile hunting ground for new physics. Some theories of quantum gravity are only compatible with a limited range of equations of state. Rule out those equations of state, and you can put a big red cross through their associated quantum gravity theories too. And astronomers may have made a big stride forward on this front in the summer of 2024. A team led by Alessio Marino, an astronomer at the Institute of Space Sciences in Barcelona, found a trio of neutron stars that are unexpectedly cold. A neutron star naturally cools down as it ages, either by directly losing heat to space or through an exodus of neutrinos that carries away some of its energy. The rate of this heat loss is directly governed by what's going on inside the neutron star and its equation of state. Marino and his team used the Chandra and XMM Newton space telescopes to study the X-rays produced by 3 different neutron stars. The hotter a neutron star, the more prodigiously it produces X-rays, and these 3 neutron stars turned out to be between 10 and 100 times cooler than other neutron stars of a similar age. This discrepancy was so drastic that it immediately ruled out 3/4 of all possible equations of state, several possible theories of quantum gravity disappearing with them. It just goes to show how crucial neutron stars are to our understanding of the universe. After all, they are the ultimate physics experiment, creating dizzying conditions that strain the very sinews of ordinary matter. And so as we approach the centenary of when they were first proposed, neutron stars remain as enigmatic, mysterious, and important as ever. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.